You know that invisible force field protecting our planet, Earth's magnetic shield? We tend to think of it as this smooth, stable barrier. But it turns out it's got a kink. Scientists have found it can reconfigure itself in these rapid, localized ways. And that discovery might just change everything we thought we knew about space weather. So, what exactly is this kink? Well, it's something called a magnetic switchback. And what's so wild about them is just how fast and violent they are. Honestly, understanding these bizarre events could completely rewrite the rulebook on how we prepare for the biggest storms the sun can throw at us. Okay, let me try to paint a picture for you. Imagine the magnetic field is a straight line pointing from the sun toward us. A switchback is when that line, out of nowhere, violently bends back on itself in a perfect hairpin turn. For a moment, it's pointing the other way before snapping right back to where it was. It's a shocking amount of change, and it happens in the blink of an eye.
Now here's where it gets really fascinating. A switchback isn't just some weird physics oddity that scientists find cool. It's a potential clue. It's a signal that the entire system protecting our planet might be behaving in a way we've never fully appreciated.
To get why this is such a game changer, we have to rewind a bit and look at the old weather report for space. You know, the way we've always thought about the risks. For decades, the thinking was pretty straightforward, right? More energy comes in from the sun, you get more disturbance here at Earth. It was seen as a simple, direct cause and effect relationship. And, you know, our whole approach to space weather has been based on that idea. For years, the alerts have focused almost entirely on magnitude. How big was the solar flare? How fast is the solar wind? The bigger the numbers, the higher we thought the risk was to our satellites and our power grids. But what if that's only half the story? Yeah, what if there's a secret ingredient we've been totally overlooking? And that brings us to this new idea, coherence. The theory that it's not just the raw power of a storm that matters, but its internal pattern and its organization. This is a massive shift in perspective. The old view was all about amplitude, basically how big is the wave. But this new view is about structure. How organized and coordinated is that wave? And that could make all the difference. So what do we even mean by coherence? Well, think of it as the exact opposite of random noise or static. It's when different parts of a system all start acting together in concert. Their changes become structured, they're linked up, and they can even be repeated over time and across huge distances. Here's the perfect analogy. Picture a giant crowd of people just wandering around a city square. It's totally chaotic, right? It's just a lot of random local noise. But now, imagine that same crowd suddenly starts marching in perfect synchronized step. The number of people hasn't changed, not at all. But their collective impact, it's enormous now. That is the difference between an incoherent system and a coherent one. And this transformation from random noise into a coordinated system, it's not always a slow, gradual thing. Sometimes a system can just snap into this new state, right when it crosses a critical line, a kind of point of no return. The classic example here is a sand pile. You can add thousands and thousands of individual grains of sand and not much happens. But then you add that one final grain and bam, you trigger a massive avalanche. The system didn't just get a little bit bigger, its entire behavior changed, all because it crossed a critical threshold. Scientists can actually model this pretty simply. Let's just imagine there's a level of organization in the system we can call K. And there's this critical threshold, Kc. The entire behavior of Earth's magnetic shield might just depend on which side of that line it's on at any given moment. So when the system is below this critical threshold, everything is pretty much business as usual. Any variations you see in the magnetic field are localized, they look like random noise, and what's happening in one place has almost nothing to do with what's happening somewhere else. But when a strong solar storm pushes the system above that threshold, everything changes. The dynamics suddenly just snap into this coordinated, structured state. And this is when events like those magnetic switchbacks might start showing up, not as random flukes, but in clustered, organized sequences.
Now, we have to be really, really clear about something here. This is not a geomagnetic pole reversal. Okay? We're not talking about the North Pole flipping to become the South Pole. This is what's called a synchronization regime shift, a fundamental change in the behavior and the organization of the system's dynamics, not its permanent orientation.
So, if this whole theory holds up, what does it actually mean for us back here on Earth? Well, it could lead to a completely new kind of warning system, one that's focused on reading the emerging patterns in the chaos. I mean, think about it. The operators of our satellites and power grids could start looking for totally new signals. They could watch for rising correlation between different sensors miles apart. They could look for repeatable patterns emerging from what used to just look like random noise. And they could see those switchbacks appearing in structured groups, a dead giveaway that the system has crossed into a more organized and maybe more dangerous state. This would fundamentally change our whole approach. We'd be moving away from just monitoring raw intensity to actually assessing structure risk. In other words, how organized is the threat? But this brings us to the most important part of any scientific idea, really. A good theory isn't just one that sounds convincing. It has to be testable. It has to give us a clear way to try and prove it wrong. And this coherence theory, it makes very specific, measurable predictions. If it's right, then as a storm ramps up and crosses that threshold, we should see correlation across sensors go way up. We should see repeatable patterns emerge, and events like switchbacks should start clustering together in time. And, just as important, when the storm passes, that coherence should just collapse and disappear. And that's the mark of a really powerful scientific model. It's not afraid to be tested. If we look at the data from our satellites and we don't see these patterns pop up during major storms, well, then the theory is wrong. This idea, falsifiability, is what separates real science from just speculation. So all of this leaves us with a pretty provocative final question. As we look to protect our technology, which is getting more fragile all the time, we really have to wonder, is the next great threat not simply the strongest solar storm we've ever faced, but the first one that is truly, deeply organized?